and welcome back to the channel. Today we are going to talk about Bernoulli's theorem. We will explore its derivation and implication in fluid dynamics. First, let's know about Bernoulli's theorem. In this presentation, we will explore Bernoulli's theorem, a fundamental principle in fluid dynamics. We will discuss its derivation, key implication, and real-world applications, providing a comprehensive understanding of its significance in various fields such as engineering and physics. Now let's know about its historical background. Bernoulli's theorem was named after Daniel Bernoulli, a Swiss mathematician who published it in his book Hydrodynamic in 1738. This theorem laid the groundwork for modern fluid mechanics and has influenced various scientific advancements in the study of fluids. Now let's discuss some basic concept of fluid dynamics. Understanding fluid dynamics required familiar with concepts such as pressure, velocity, and density. These parameters interact with the fluid flow, influence its behavior, and enabling us to apply Bernoulli's theorem effectively in particle scenarios. As we know what is pressure, velocity, and density, we can move further. Let's see the statement of Bernoulli's theorem. Bernoulli's theorem states that for an ideal incompressible fluid, the sum of pressure energy, kinetic energy, and potential energy per unit volume remains constant along a streamline. This principle is fundamental in understanding fluid behavior in motion. Derivation of Bernoulli's equation. The derivation of Bernoulli's equation involves applying the principle of conservation of energy to a fluid element by considering forces acting on the fluid and integrating over a streamline. We can arrive at the mathematical expression for Bernoulli's theorem. As you can see the theorem, how it is derived in this image. Now let's move on to the assumption in Bernoulli's theorem. Bernoulli's theorem is based on several assumptions. The fluid is incompressible, non-viscous, and steady state. This assumption simplifies the analysis but may limit the theorem applicability in certain real-world situations where these conditions do not hold. Now let's discuss the application in engineering. Bernoulli's theorem has numerous applications in engineering, such as in the design of airfoils, piping systems, and hydraulic machinery. Understanding these applications help engineers optimize design for efficiency and safety in the fluid system. Implication in aviation. In aviation, Bernoulli's theorem explains how air pressure difference create lift. The shape of an aircraft wing causes air to travel faster over the top surface, resulting in low pressure and enabling the aircraft to rise. Limitation of Bernoulli's theorem. While useful, Bernoulli's theorem has limitation. It does not account for viscous effect and turbulence, and is primarily applicable to ideal fluids. Understanding this limitation is crucial for accurate analysis in practical fluid dynamics. Real-world examples. Real-world examples of Bernoulli's theorem include Venture meters, which measures fluid flow rates, and atomizers, which spray liquids by creating a low pressure area. This example illustrates the theorem's practical significance in everyday application. Now let's discuss what are the future research and directions. Future research in fluid dynamics may explore the extension of Bernoulli's theorem to more complex fluids, including non-Newtonic fluids. This could lead to advancement in various fields, including biomechanics and environmental engineering. Finally, we come to the conclusion that Bernoulli's theorem is a cornerstone of fluid dynamics that offers valuable insight into fluid behavior. Understanding its derivation, implication, and limitation is essential for applying this theorem effectively in both theoretical and practical contexts. Thank you guys. That's it for today and see you next time with another topic.